Have you ever noticed how milk spoils faster in summer than in winter? That's temperature at work, speeding up chemical reactions invisibly all around us. So, why does temperature have such a dramatic effect on how fast a reaction occurs? Well, at higher temperatures, molecules move faster, collide more often, and with greater energy. And here's the crux: only those collisions that occur with enough energy, more than a certain threshold called activation energy, actually result in a chemical reaction. So, as temperature rises, more molecules gain this required energy and the reaction speeds up. Think of it like heating popcorn. Not every kernel pops at room temperature, but once it gets hot enough, boom! Reactions happen rapidly. Now let's visualize this. Imagine an energy distribution graph where at higher temperatures, a larger area lies above the activation energy threshold. That's the temperature advantage in action. Now that we know temperature increases reaction rate, let's make it mathematical. Enter the Arrhenius equation, K equals A times e to the power minus Ea divided by RT. In words, the rate constant K equals the frequency factor A multiplied by an exponential term that involves activation energy Ea, the universal gas constant R, and the temperature T in Kelvin. The exponential part explains the fraction of molecules having enough energy to react. So, as the temperature goes up, the negative exponent becomes less negative, the exponential term increases, and hence, the value of K shoots up. That means the reaction becomes faster. Whether you're manufacturing chemicals or understanding enzyme behavior in the human body, this equation is your guiding compass for rate predictions. Let's take this further into visuals. What if you wanted to determine the activation energy of a reaction in a lab? That's where plotting comes in. If you take natural logarithm on both sides of the Arrhenius equation, you get ln K equals ln a minus Ea divided by R into 1 over T. This gives you a straight line equation, just like y equals mx plus c, where ln K is plotted on the y-axis and 1 over T on the x-axis. The slope of this line is minus Ea by R. So by calculating the slope, you can figure out the activation energy. This linear graph is immensely helpful in both research and industry to decode kinetic behavior without diving directly into molecular collisions. But what exactly is this activation energy we keep mentioning? Well, it's the minimum energy a reacting molecule must possess to overcome the barrier and convert into product. Think of it as pushing a boulder up a hill. Only if you give it enough energy to reach the top will it roll down the other side. In energy profile diagrams, the difference between the reactants and the peak of the curve is your activation energy. The reaction may be exothermic, releasing heat, or endothermic, absorbing it, but the activation energy is required either way. The transition state, or activated complex, lies at the top of this hill, representing the short-lived configuration before the product is formed. This is where the magic happens, even if just for a fleeting moment. Now here's a twist. What if you didn't want to increase temperature but still wanted a faster reaction? That's where catalysts come in. A catalyst provides an alternate pathway for the reaction, one with lower activation energy. So, even at the same temperature, more molecules now have enough energy to cross the barrier. It's like carving a tunnel through a mountain instead of climbing over it. The reaction goes faster, but the catalyst itself remains unchanged. This principle is the reason why catalysts are so widely used, from the catalytic converters in vehicles to enzymes speeding up reactions in our bodies. They help reactions proceed efficiently, even at moderate temperatures. And no, they don't change the overall enthalpy or del H of the reaction, just the energy hill that needs to be climbed. Let's apply what we've learned with a quick numerical. Suppose the rate constant Kelvin at 300 Kelvin is 1.6 times 10 to the power minus 3 per second, and K2 at 310 Kelvin is 4.8 times 10 to the power minus 3. To calculate activation energy, we use the equation ln of K2 by Kelvin equals EA by R multiplied by the difference of T2 and T1 divided by T1 into T2. Plug in the values. Ln of 3 is approximately 1.098. Multiply that with our equal to 8.314 and temperatures and solve for EA. You get EA approximately equal to 85.1 kilojoules per mole. That's a solid example of how just a small rise in temperature can significantly boost the rate of a reaction. Let's quickly revisit what we've covered. Temperature has a direct effect on how fast chemical reactions occur by increasing the energy and number of effective collisions. The Arrhenius equation gives us a mathematical model for this, connecting the rate constant with activation energy and temperature. A plot of ln K versus 1 over T helps us graphically extract the activation energy. Catalysts offer a smart alternative, lowering the energy barrier without altering the heat exchange or equilibrium. These concepts aren't just academic, they fuel industrial reactors, preserve food, optimize enzyme activity in our cells, and much more. I hope this session helped you see how chemical speed is a finely balanced dance of energy, temperature, and catalysis. Catch you in the next topic where we explore more fascinating aspects of chemical kinetics.